Hello and welcome to comp452 computer architecture. So you can see the data path that we have developed so far, and this data path is complete for R-type instructions that we want to implement, and it is also complete to implement or to execute load word and store word instructions. Now we are left with one instruction that we want to implement in this discussion, and that instruction is branch if equal. So let's quickly talk a little bit about branch if equal, and then we'll come back to this figure and add the necessary blocks and lines, circuits to add support for executing branch if equal instruction. So branch if equal instruction branch if equal instruction, let me give you an example. I actually wrote a small piece of code, and this is the branch if equal instruction that I had in that code. Oh, I'm sorry. Loop. So when I assembled this instruction, the instruction code that I got was this 0 hex and 1600 1600 and FFFA FFFA. And this instruction in my program, it was located at instruction memory address of this instruction. This branch if equal instruction was 0 hex 0040 0018. This was the address where this instruction was placed by assembler. Okay. Now let's take a look at this instruction in more detail, and I'm going to draw 32 bits. So okay, now each of these is 4 bits. I should have drawn it ahead of time. That would have saved me some time here. But anyway, let's draw it, because we want to be very clear about this before we start adding blocks, hardware blocks. Okay, now the instruction code is this 1600FFFA. Okay, so now what I'm going to do is I'm going to write the bits in different color, and which color should I choose? Let's choose this green color. Okay, so this one is 0001, 0001. Then we have 6, which is 0110. Then we have 0, which is 0000. We have another 0, 0000. Then we have F, it is 1111. Another F, 1111. Then a third F, 1111. And then we have A. A is 1010. Now let's break it up into its parts. So this is the opcode, and this is the opcode for branch. And then next 5 bits, these are our S register, which in our case is S0. Then we have next 5 bits, which is RT, which in our case is register 0. And then we have this 16-bit offset. 16-bit, actually I should not write offset, I should write 16-bit 2's complement number. 16-bit 2's complement number. Or even better, it would be that if I say that it's a 16-bit number in 2's complement format. Okay, it's one and the same thing. You know what I mean. 16-bit 2's complement number. Okay. Now, how this instruction is executed, because this will tell us what hardware do we need. Okay, now what happens is that the main controller looks at the opcode. From opcode it knows that it's a branch if equal instruction. Then it looks for RS and RT. And since RS and RT register values, by the way, since RS is 1 followed by 4 zeros, so it is register 16, and RT is register 0. So it presents the register numbers to the register file, and register file outputs the values in those registers at its output port. So here you get 1 followed by 4 zeros. Here you get all 5 zeros. So here you get the value of our S register. In our case it's going to be S0, and here you get the value of RT register, which in our case is going to be the value in 0 register, which is 0. Okay, so then what it does is these two values, they go to the two inputs of ALU. Okay, and next it performs a subtraction operation. Okay, because it wants to test whether the two registers are equal or not, so it performs a subtraction operation on the value stored in register S0 and the value stored in register 0. And when it performs the subtraction operation, there is one output which we call the zero output of processor. This zero output. This is the zero output of processor. Sorry, not the processor, but the ALU. I'm sorry, I take back my words. It is the zero output of the ALU, and and also it programs the ALU to perform subtraction operation. So it subtracts if the result of that subtraction operation is 0, then this flag, this line will be asserted, or it will become active high, or it will become high. And now it knows whether the branch is to be taken or not taken. If it is high and the instruction is branch instruction, then the branch is taken. So basically the signal goes into an AND gate. This zero signal goes into an AND gate, and the other signal comes from main controller, and this signal, if this signal is 1, it means that the instruction is a branch instruction, and if this 0 signal is 1, it means the result of the subtraction operation is 0. So when you do both, when you add both of these values, you get a signal which determines whether the branch is taken or not taken. Okay, whether the branch is taken or not taken. Okay, so if the output of this blue AND gate is 1, then it means the instruction is a branch of equal instruction and the branch is taken. Okay, now what happens? Now comes the role of this number. Now comes the role of this 16-bit number in 2's complement format. What does this number tell you? This number, this 16-bit number, is the number of instructions to jump forward or backward relative to current value in program counter. Okay, relative to the, actually I should not say this, there is a reason. Relative to PC plus 4, and I'll show you in a minute why it is PC plus 4. So basically, if this is a negative number, then we jump backwards. If it's a positive number, we jump forward. Okay, I took a short break because I wanted to look up something related to usage. Okay, now in this case, what's happening is that we have this number which is FFFA. So what does this mean? Okay, Okay, let's see. The number of instructions that we have to jump relative to PC plus 4 is, uh, let's write it here, F F F A, triple FA. Okay. Triple F A. Now, is this a positive number or a negative number? Yes, you know, is a negative number. Negative number. It's a negative number. Okay. Why it's a negative number? Because its most significant bit, which is bit 15, is 1. So what will be its value? Its value is minus 1 multiplied by 2 raised to power 15 plus 1 into 2 raised to power 14 plus so on, plus 1 into 2 raised to power 3 plus 0 into 2 raised to power 2 plus 1 into 2 raised to power 1 plus 0 into 2 raised to power 0. Now if you calculate the value, it will come out minus 6. So what this means is that we have, or maybe we should say the execution has, we have to jump 6 instructions back from PC plus 4. We have to jump 6 instructions back from PC plus 4. Okay, but how do we do that? The first thing is that every instruction is 4 bytes long, so it means we have to jump 6 into 4, which is equal to 24 bytes before address PC plus 4. Now here addition operation comes in very handy. So we multiply minus 6 by 4 and we get minus 24, and minus 24. Then we represent minus 24 as 2's complement number in 32 bits. Okay, and finally we add this number to PC plus 4, which is available to us. This PC plus 4 is available to us. Yeah, look, this is where it's available to us. PC plus 4. This is PC plus 4. It is available to us. So basically, what is this multiplying by 4? in binary numbers, if you want to multiply a number by 4, all you have to do is to shift left the number by 2 bits, because 4 is equal to 2 raised to power 2. Okay, if you want to multiply a number by 8, you have to shift it left by 3 bits, because 8 is equal to 2 raised to power 3, and so on. Okay, so basically what we need to do is, these are the steps that we need to perform, or the processor needs to perform. Number 1, convert the 16-bit number to 32-bit number, preserving the sign, So this clearly means that we want to run it through sign extender. In other words, pass it through sign extender. Okay, we already have that sign extender. Look, there we go. This is our sign extender. Okay, this is our sign extender. So we just have to pass it through sign extender. Okay, and the good thing is that this sign extender is already getting that number, this number from here to here. It is already getting that number, because these are bits 0 to 15 of the instruction code. They are already going into the sign extender. Now, then what else do we have to do? It turns out that we don't have to do much, and we just have to add a little more hardware. Let me carefully erase this, and let me carefully erase this, and then let me add the lines as they were. Basically what we have to do is we have to shift left the address by, we have to shift left the output of sign extender by 2 bits. Okay, so the second thing that we need to do is shift left sign extender output by 2 bits. This is equal to multiplying the number by 4. Okay, so what we do is we come back here, and okay, look, this was the number which was going into, this number was going into the lower input of ALU source mux. So we take it out, take this line from here, we bring it here, and we pass it through shift left 2 bits. Okay, so now now this number has been multiplied by 4, and since if we input a negative number here, we get a negative number here. If we input a positive number here, we get a positive number here. Okay, now our task becomes much easier. Now what we want to do is we want to add this number to the value of PC plus 4. So what I'm going to do is I am going to erase this stuff, and I am also going to actually, I should not have erased it. Yeah, I think I should have erased it. And I'll redraw the figure, the parts of the figure later on. So we want to get this value, and we want to uh, pass it to uh, to an adder. Adder. ADD adder. So now this output is PC plus 4 plus this number which we obtained by shifting left. Well, shift lefting doesn't make any sense. By shifting left 2 bits, the output of sign extender. Okay, so this is the output of sign extender, and we run it through shift left combinational circuit. Actually, it outputs the number which is a product of 4 and the original number, or the original number multiplied by 4. Okay, so now we want, if the branch is taken, we want this address to go to the program counter, and we do not want PC plus 4 to go to the program counter. Okay, so it means that we have to add a multiplexer here. Okay, so let's do some cleanup before we can draw our next multiplexer. And we also have to disconnect this line, and you will see in a minute why I have done that. And like this. Okay, now here we need another multiplexer. Oh, I'm sorry, I should have changed my writing tool. So this is another multiplexer, and one of its inputs is this number, and its other input is this number, PC plus 4, and its output is routed back to program counter. Okay, got it? So this is very important. So main controller asserts this line if it's a branch instruction, and if the output of ALU, if the result of ALU is 0, then this line, the 0 output line, is asserted. So if both these inputs to AND gate are 1, then this line is asserted, and in this case the new address, the branch target address, it goes to the program counter. Okay, so let's write this thing here. Shift left sign extender output by 2 bits, and now we go to the next page. Okay, number 3, add output of shift left module and PC plus 4 result goes to a multiplexer, to a mux. Actually, let's say to a 2 to 1 mux, 2 to 1 mux, which is 32-bit wide, 32-bit wide. Other input of the mux, other input of the mux is PC plus 4. Other input of the mux is PC plus 4. And if instruction is branch if equal and the result of subtraction operation on the two registers is 0, then the branch is taken. And the branch target goes to PC, and PC plus 4 doesn't reach PC. Okay, so these are the steps. So you can see that. Have we written everything? I think we have written everything. So the first step is convert the 16-bit number to 32-bit number, preserving the sign. In other words, pass it through the sign extender. Then shift left sign extender output by 2 bits, and then add output of shift left module and PC plus 4. We did that. This is where we are doing this. We are adding PC plus 4 and the output of shift left 2-bit module, and the result is going into this multiplexer, and the other input of the multiplexer is coming from PC plus 4. And if main controller asserts this line, it means it's a branch instruction, and the main controller also programmed our main ALU to perform subtraction operation on this S0, the value in S0 and the value in 0 register. Okay, and if the result is 0, then this 0 line will be asserted, or it will be activated, or it will become high, and both inputs of the AND gate will become 1, and as a result this input will become 1, and this select line will become 1, and the 1 input will go to the output, which is the branch target, and the branch target will be loaded into program counter on the next clock cycle and that is where the execution will resume. So I hope that I have been clear in adding these, in explaining the implementation of branch if equal instruction, and it's also beautifully explained in your book, Patterson and Hennessy 5th edition. So, but still, if you have questions, you are most welcome to ask me, and also please point out any mistakes or any shortcomings in the lecture. And now we are going to stop, and with this we have completed our discussion of data path. Let's write it here. Data path is complete. Which color should we use? Let's use the good green color. Data path is complete. Okay, very good. So now we are going to start working on implementing the controllers. So let's go back and let's stop here. By the way, I want to tell you that your textbook contains some beautiful examples of how this data path implements load word instruction, how it implements store word instruction. Rather, I should say that how load word instruction flows through this data path, and how store word instruction flows through this data path. And you must read those pages. And if I can, yes, I think I can, I'll tell you the page numbers that you have to read. So if you read those page numbers, I'm sure you will learn this stuff very clearly. What is it saying? It is saying that the file that I tried to open is not available. That's not good. So let me, actually, let me open the file and let me tell you the page numbers that right. So you have to read from page 251 to 258. So let's write it here. Read page 251 to 259. This contains full discussion of the data path with several examples. Especially look at the figures. Figure 4.11. Figure 4.11. Now this figure is that of the data path. Okay. This figure is that of a data path, and I just realized that I should have written that this is called PCSRC line. This line is called PCSRC, PC source. Alright, so now it's time to stop, and there we go.